8.4 vector and parametric equations of a plane. Okay, so we have done vector and parametric equations of a line. Okay, now we're going to go on to a plane. So as a recall, planes are flat surfaces that extend infinitely far in all directions. Okay, we usually denote them by a parallelogram, just to show like the way that they are, like their angles, right? The way that they are leaned, I guess. Okay, so planes are usually represented by parallelograms with the understanding that the plane will extend in all directions. Okay, even though the parallelogram is closed, we have to you have to know that these extend in all directions forever and ever. Okay, and we represent a plane with the Greek letter pi. Okay, so pi in this case is no longer 3.14, it's just like a representation of a plane, that's it. In real life, a plane may be represented by, these are like visuals of it, okay, the top of a desk, a wall, or an ice surface in like a hockey rink. Okay, planes can be determined if we're given the following. Okay, so here's the thing. In order to solve for the equation of a plane, we need, and if you take a look at these four, I'll leave this, these four diagrams, we either need a line and a point, okay, and think about it, the line has a direction vector and it has another point for us, right, if you think about it, okay, 3 points, right, between 3 points we can get actually 3 direction vectors if you think about it, and then we have 3 points, right, we can do A, B, B, C, C, A, all 3 different direction vectors, right? So these are just some of the things that we need, okay? 2 intersecting lines. Again, we have multiple points and direction vectors. Or we need 2 parallel and non-coincident lines, okay? So 2 parallel, they're pretty much called distinct, right? So the lines will never touch. If we're given any of these combinations, we're able to find the equation of the plane. Okay, so in r cubed, so that's 3D, if the vector r naught equals xyz is determined by a point on the plane, and vector A is A1, A2, A3, and vector B is B1, B2, B3, are direction vectors, then the vector equation of the plane r equals r naught plus SA plus TB. Okay, so here's the expansion here. We already had 1 parameter and a direction vector. For a plane, we're going to extend it to 2 parameters, 2 direction vectors. The only difference. Okay, so from here to here, remember, these 2 are equivalent. They're just written a little bit differently, but they are both vector equations. Okay, so with x, y, z plus a parameter and then a1, a2, a3, that would be a line. We extend it now by a parameter and another direction vector. Now it's a plane. Okay, and the parametric form is going to be the exact same thing. So we're going to have x equals y equals z equals. We're going to stack the points first, and then, oh, that's supposed to be A3, SA1, SA2, SA3, and then TB1, TB2, TB3. Okay, so this is the parameter and the first direction vector. This is parameter and the second direction vector, and S and T are elements of the real number system. Okay, and then just note there are no symmetric equations of a plane. Okay, so note, we must have 2 unique direction vectors. Unique meaning they're not scalar multiples of one another. Okay, they're completely different direction vectors. Okay, and 2 parameters, right? Like, so in this case, S and T, to form the equation of a plane. Okay, so the 2 parameters means that the plane is 2-dimensional. Okay, also note, replacing the parameters in the vector and parametric equations of a plane with numbers, okay, generates points on that plane. because what you can do is you can replace the s and the t with infinitely many numbers, and there's going to be an infinite number of points that lie on the plane. Example 1a. Determine a vector equation and the corresponding parametric equations for the plane that contains these 3 points. Okay, so as a review, when we're talking about a vector equation, okay, we need RO plus S. We can say D1. Okay, we can say D1 plus TD2. Okay, and remember S and T are elements of the real number system. So let's find the direction vectors first. So let's go ahead and find direction vector AB. Okay, remember this is B minus A. So -1 minus -1, comma 1 minus 3, comma 0 minus 8. So we have 0, -2, -8. That's going to be one of our direction vectors. Okay, I want to point this out. Direction vectors can be scalar multiples of one another. So if we actually wanted to simplify this, we could divide this by 2, and we could get the direction vector 0. Oh, you know what? I'm going to divide by -2. Okay, we get 0, 1, 4. These direction vectors are going to be in the same direction. They're just going to be scalar multiples of one another. Okay, so 0, 1, 4 is the simplest form. Now let's find another direction vector. Let's try BC. Okay, so we're going to go C minus B. 4 minus -1, 1 minus 1, 1 minus 0. Okay, so we get 5, 0, 1. And there's no number that we can divide all 3 of these by and still get integer values, so that's fine. So that's it. Let's write out our vector equation. So pick a point first, A, B, or C, it doesn't matter. I like to avoid negatives, so I'm going to write C, which is 4, 1, 1. Okay, but if you wrote A or B, still the correct answer. Okay, plus parameter S times either one of these direction vectors. It doesn't matter. Okay, 0, 1, 4. I'll just go in order. Okay, and then 5, 0, 1. So plus T, 5, 0, 1. Okay, now converting to parametric, we're going to work with x equals, y equals, and z equals. Okay, if you want to stack them, we're going to do them in order. So 4, 1, 1. So 4, 1, 1. Because we know that this is the x, this is the y, and this is the z component. Okay, now s is x, y, z. Same idea. So 0s, 1s, 4s. Okay, plus we could write 0s. I'm not going to write that. I'm going to skip it. Okay, plus 1s plus 4s. Now, same thing for the third part here, x, y, z. Okay, so plus 5t, 0t, 1t. So plus 5t, 0t I'm going to leave out, and then plus 1t. So these 3 are the parametric equations of the plane. Okay, now B. Do either of these 2 points, P or Q, lie on this plane? Okay, so it's going to be part B. So what we want to do is first let's do the first one. So we're going to check P 14, 1, 3. So what we want to do is we want to check this in the parametric equations. So if we want to reference them, they're right here. So let's go x equals 4 plus 5t, and then we're going to have y equals 1 plus s, and then we're going to have z equals 1 plus 4s plus t. Okay, so we're actually able to check these very easily because we have an equation for x that only has a parameter t. So the s was 0. So let's go ahead and sub in 14 and let's solve for t. Okay, so bring the 4 over, it becomes -4, so 10 equals 5t. Divide both sides by 5, and we get t equals 2. Now, same idea for y. Y only has the parameter s in it, so this is easy. Sub in 1 for y, bring the 1 over, so it becomes -1, so I get 0 equals s. Okay, so now that I have a t and an s, what I want to do over here is I want to plug them into here, okay? So let's say z equals 1 plus 4s plus t. So 4 times 0 goes away, and we get 1 plus 2, and we get z equals 3. This part here is our check. These two parts we solved for. So what you solve for is never going to change. Like, that's mathematically correct. Now we checked these in here, and now we just cross-reference, okay? Does z equal 3? Does the parameter t equals 2 and s equals 0 actually hold? Yes, it does. So therefore, yes, the point lies on the plane. Okay, now let's check Q, 14, 1, 5. So very similar, but a little bit of a different approach here, okay? So we're still going to check 14, 1, 5. Okay, so obviously when we sub in 14, we're still going to get t equals 2. That's going to hold. Obviously when we sub in 1, we're going to get s equals 0. That's going to hold. Now, here's where the difference comes into play, okay? We have to check the 5. So z equals, okay, we have the 1 plus 4, 0 plus 2 again. We're going to equal 3. So this is just showing the difference between these two. If you get a point that actually lies on the plane or a point that doesn't lie on the plane. So since we get z equals 3, so the exact same 3 steps here, when we compare it, we see that if we have the parameters t and s, it will not punch out the z equals 5 that we were looking for. So that's what the difference is going to be when you get those two types of questions. So 14.15 does not lie on this plane. Example 2, a plane pi has r equals, so this is going to be the the vector equation of this plane, 6, -2, -3, plus the parameter s and a direction vector, plus the parameter t and a direction vector. Okay, and s and t are elements of the real number system. So the plane has this vector equation as its equation. Now our task is to determine the point of intersection between pi and the z-axis. Okay, so first what I'm going to do is I'm going to write the parametric equations of this plane. So 6, -2, -3 plus, and I did pluses all the way down here because all of these values here for s are positive. So I'm going to take that back. Okay, plus 1s, so just plus s, plus 3s, and plus 0s I'm not going to include. That's why I deleted the plus sign there. Now for the t value, so we have plus 2t, we have plus 2t, and we have minus 1t, so minus t. Okay, so we have parametric equations, that's what we're going to use. Now, let's talk about the z-axis. Okay, so the z-axis can be denoted as 0 in the x direction, 0 in the y direction, and hitting every z value. So what we're going to do is we're going to sub in 0, 0, and then z. Okay, so let's take the x equation. X equals 6 plus s plus 2t. What we're going to do is we're going to sub in 0 for x. 0 equals 6 plus s plus 2t. Okay, I'm going to leave it there for 1 second, and I'm going to come back to it. Now, we're going to also sub in 0 for the y. So we have y equals negative 2 plus 3s plus 2t. So let's go ahead and sub in 0. Negative 2 plus 3s plus 2t. So when we don't have zeros in many of the parameters where we can just simply calculate, we're going to get equations with two parameters, like two unknowns, s and t. Okay, so in this case, we have two equations, two unknowns. So I'm just looking at the coefficients of the equations. I'm thinking to myself, I know for two equations, two unknowns, I'm going to have to use either substitution or elimination. Okay, so in this case, I'm a substitution type of gal. You can use elimination if you want, but I look at this s right here as though it has the coefficient of 1. So what I'm going to do is I'm going to bring over the 6 and bring over the 2t to the other side. So we're going to have negative 6 minus 2t, and that's going to equal s. Okay, by using the parameter, if you get a parameter with the coefficient of 1, what ends up happening is you're not going to have to deal with fractions, right? Because we're not dividing out in order to isolate for s. Okay. So then what we do is, again, two equations, two unknowns. We're going to substitute this s into where the s is in the second equation. So let's go ahead and go 0 equals negative 2 plus 3. I'm going to substitute in the s, negative 6 minus 2t, and then plus 2t. Now we have one equation. The only unknown that we have is t, and now we can solve. So let's go ahead and distribute into 3. So we have 0 equals negative 2 minus 18 minus 6t plus 2t. Okay, so let's collect these. Let's collect these. We have 0 equals negative 20 minus 4t. So my thing is that I don't like to divide by negatives. I think that we get confused a lot of the times. So I'm going to bring this negative 4t to the other side so that we can just simply deal with the leading coefficient of positive 4. Okay, and we get t equals negative 5. Okay, so remember, with substitution, we isolate. Okay, so isolate, we sub into the other equation, we solve, and then what we end up doing is we substitute the t back into the first equation to solve for s. So we have s equals negative 6 minus 2, and then the t is negative 5. Okay, so we have negative 6 plus 10, so s equals negative or plus 4. Okay, so we have just solved for the parameter of s and t that would allow for our equation to yield 0 and 0 for the x and the y. Okay, so since we know the parameter s and t that satisfy our point 0, 0, okay, what we can do is we can take those two parameters, substitute it into the z equation, which is negative 3 minus t, and then we can actually solve for what our z value would be, right? Because we're talking about the point of intersection, okay, of the z-axis. So z equals negative 3 minus negative 5, which is negative 3 plus 5, which is 2. So at the end of the day, the point of intersection is z equals 2. Oh, sorry, z equals 2, yes. I'm going to write it as an ordered triple, 0, 0, 2. Example 3, determine the vector and parametric equations of the plane containing this point, okay, and this line. Okay, so now we have a point and some line. Okay, so what are we given by being given a point and a line? Okay, so we actually have information about 2 points. We have the point 1, -5, 9. And we have the point 1, 1, 1. Okay, if this question tells us that our plane includes this point, so that's included. And if our plane includes this line, then 1, 1, 1 obviously also is included on our plane. Okay, so let's find a direction vector between these 2 points. Okay, so direction vector. Let's go 1, -1, 1 -5, 1 -9. Okay, the difference between these 2 points. So we're going to have 0, 6, -8. Okay, again, there is a scalar multiple that we can divide by in order to reduce this, and it's -2. No, let's just do 2. Okay, 0, 3, -4. So just throwing it out there, if we did do -2, this number, which is our leading number, because our leading number is 0, so we automatically go to the next number. Okay, but this is our leading number to look at. We want that to be positive. Okay, so 0, 3, -4. Okay, what else does the question give us? The question also gives us another direction vector, which is here, -1, 1, 0. Okay, so this is all the information that we need to determine vector and parametric equations. So vector equation, put a point. You can use either point 1, -5, 9, or 1, 1, 1. Doesn't matter. Okay, I kind of like 1, 1, 1. It's nicer. Okay, then we're going to use 2 direction vectors such that S and T are elements of the real number system. So our first direction vector is 0, 3, -4. Doesn't matter what order you put these in. Okay, and our second direction vector is -1, 1, 0. Again, if you don't like this leading number to be negative, you can find that scalar multiple, which would be 1, -1, 0. You could just divide each of these by -1, and it still works. Okay, now parametric equations. Let's do like the stacking method. Okay, so the point is 1, 1, 1, 1, 1, 1. That's it. Okay, let's apply the first parameter. So ignore the x. Now we have 3s. And we have a -4s. Okay. And the last one, -1t, 1t, and then we ignore the last one. -t plus t, ignore. Okay, so here is the vector and parametric equations. Just as a little tidbit, 1, -5, 9 would have also worked, which would have change these numbers here, and then these can also interchange, and so could the parameters. You could use different parameters as well. Okay, but it doesn't matter.